Welcome to a little, who am I kidding, not little. It's going to be a lengthy look at forces or dynamics, however we like to call it, Newton's laws, third way of discussing it, in order to get ourselves a little bit more prepared for AP exam. What I've got here is not necessarily everything you could possibly ever look at, but it's some of the problem solving techniques. And while we will be looking at problem solving from an equation mathematical standpoint, I will try to point out some places where you can think of comparisons. What if one variable got bigger, another variable got smaller? How would that affect the overall motion of an object or the acceleration of an object? But we'll start off with our good old friend, Newton's laws of motions. First law says that if if you have some forces acting on an object, if they're balanced, there'll be zero acceleration. And third law says that for every interaction, forces are equal in size and in opposite direction. So sometimes it feels like there's a bit of a disconnect there, but you will get an acceleration if the outside forces on an object are unbalanced. And when that occurs, you will get an acceleration that's proportional to that net force that's acting on the object. So if I push with a force of 20 newtons on the right side of an object, it will push back with 20 newtons on me. But I'm only applying one force to that object. From the outside, it is a 20 newton force. If there's nothing else resisting any motion, that 20 newtons acting on it will be the net force. If we take an approach from looking at its forces coming from the right or from the left, up versus down, opposing forces will subtract from each other. Forces that are in line with each other will add and will create a larger net force. But that net force that acts on an object can be calculated as m times a, or as opposing forces subtracted, like forces added together. So whenever we're dealing with a problem where forces, pushes, pulls are on an object, we need to do a few things. Is it already accelerating? If it is, then we need to know what direction we want to call that, positive or negative. We identify all the forces acting on the object and all their dimensions. As I just mentioned for step one, figuring out positive and negative signs. We, by standard, say that up is positive, down is negative, and so on, but there's no reason you can't flip it around if you would prefer to. Once we got those dynamics equations set up, then we can solve for whatever's needed. It might be a conceptual question that's asking us to think about the effect of a force, but it also might be a mathematical problem like the one I've got right here. Let's say I have a 4 kilogram block that has a 10 Newton force being applied to it via a rope, as shown. There is some frictional force acting on the object resisting its motion, but it has an acceleration of 2 meters per second squared. So it is accelerating towards the right. There's a force acting towards the right. If this were accelerating, if this had an acceleration of 2 and a mass of 4, it should have a net force of 8. Well, I'm applying a force of 10, so that means something's working against me. That's where that friction is going to pick up some of the force. So we want to try to solve this to figure out what the coefficient of kinetic friction is, mu s. Now I'm going to add in, because these are some older notes, I'm going to add in the capital F sub F for friction, because that's how it's written on the AP exam equation sheet. So let's go ahead and start by drawing a little free body diagram for this. What are the forces that are acting on this object from the outside? I have the applied force F. Let's label that as capital F. I've got a friction force, F sub little f. I should have a force of gravity acting on it, which I'll just call mg, and a normal force acting straight up. Those are all the forces that are acting on this object from the outside. No components, just the forces in the direction they're acting. Once we've got this established, we know it's not moving up and down, just side to side. So we only need to care about a net force equation in the x direction. So sigma f sub x would be equal to all the forces going to the right, in this case, the pull force on the rope F. And then we would technically add to it any other forces, but since the force of friction is going to the left, we assign that a negative sign. So we're going to add a negative friction force, which would be subtracting the friction force. And all that will be equal to m times a in that x direction. So we have a dynamics equation set up to describe the motion of this object, or the forces acting on it that's causing its motion. we know the pull force, we know the mass, we know the acceleration, so we can figure out what the friction force is, and then we can use the equation for the force of kinetic friction in order to figure out what the mu value is. Now in this case, we're on a horizontal surface, so we don't need to think anything too crazy. In the vertical direction, the normal force will just be equal to the weight force, m times g, so we can begin substituting and solving. We have pull force F minus mu times m times g should be equal to m times a. We got everything we need to know except for that mu value. That's our question mark. Now, before we go ahead and find the solution, which we can do, we know all the other numbers, you can start playing with the idea in your head of, well, what if the mu value is really, really big? At some point, if this number is too big, then this whole term in the equation, the friction force would be larger than the pull force, in which case we can't have a negative net force when friction is one of the two. At that point, it just wouldn't move. This is the coefficient of kinetic friction, and this is a force of kinetic friction, which means it will only exist while the object is actually in motion. If at any point this pull force is equal to or lesser than whatever the kinetic friction would be, it doesn't move anymore. So if this got smaller and smaller, we'd end up with no friction. We'd get a greater acceleration because we're subtracting less from our effort. But in this case, let's go ahead and solve for the problem. I will go ahead and move some things around here. We'd have mu k times m times g would be equal to our pull force minus m times a, and then we can divide by m and g. Now we can put in some numbers and we can calculate an answer. Now in this case, you could also use 10 for the acceleration of gravity instead of using 9.8 if you wanted to do a little bit of mental math. But I don't want to do mental math, so I pop into my calculator and I get a coefficient of friction of 0.051, but we'll just stick to 2 decimals. Now remember, there's no units on the coefficient of friction, it is just a number. Now what if we wanted to approach a problem that's similar without any numbers? We just want to look at it from an analytical standpoint. And what if we mix it up just a little bit by, instead of having the force applied parallel to the ground, and therefore parallel to the force of friction that might resist it, what if we have it applied at some angle theta, oops, went too far there, some angle theta above the horizontal that will modify things. We want to draw a free body diagram for it. We want to write out those dynamics equations for the x and the y direction, and from there we could potentially set up some sort of solution for what the acceleration of the object is. Now, before we do that, and I would like you to go ahead and try drawing this out and pause it in order to begin your own work, and then I will flash up the answers. I'm not going to make you watch me do all that, but if I'm applying a force parallel to the object, I'm going to get the most out of my force. My effort is in the direction this object should be moving. As soon as I add a little bit of angle, whatever this theta happens to be, if it's not 0 degrees, some of my force is not going to be directed in the intended direction of motion. I'm going to be applying some force, component of which that is going to be trying to lift the object. That's going to do 2 things. Number one, it's not going to be putting as much effort into making the object move forward, so I would anticipate less acceleration. However, by lifting up a little bit, I'm also going to take a little bit away from the normal force that contributes to friction. So I'm pulling with less force forward, but I'm also going to be experiencing less friction. It's kind of hard to wrap your head around exactly at what point it becomes easier to move something or harder to move something, because maybe I'm not pulling with as much forward force, but I also have less friction. But if you lift it too big of an angle, you're just going to pick the thing up off the ground, right? So you're not going to be helping the thing go forward. So we can't answer that question directly right now without taking a look at the equation. So let's start by having you pause this video and then draw yourself a little free body diagram for all the forces that should be acting on this. No components, just the actual forces. And voila, there's my solution. You should have something similar to this. A lot of times people forget about the normal force. You should draw the forces proportional to what they should be. It's kind of hard to get that perfect, but the vertical component of my pull force and the normal force are both fighting against gravity, so I don't have it drawn perfectly here, but it's a pretty good idea. Once we get that set up, then we can start worrying about dynamics equations in the x and the y direction. And we can draw those out and we can try to figure out what's there and what's not. At this point, you do want to go back to your original drawing and try to include components of the force, because you cannot work with forces, velocities, anything that are at angles to coordinate systems very easily. You have to have everything lined up with some sort of x and y axis in order to make it function. So I would have f sine theta as a y component, or a vertical component in this case, of my pull force, and I'd have f cosine theta could represent a horizontal component of my force. So let's go ahead and write out some dynamics equations. Give them a shot. I'll pause the video here, and when you're ready, unpause it and see what you get. All right, so here's my solutions. Not solutions, sorry, just the equations. In the horizontal direction, which is the x-axis for us, we've got f cosine theta, the x component of our pull force, minus friction should equal to some m times a. We don't know what the acceleration is just yet, but we have to put something in there. And if I'm pulling towards the right, the acceleration is going to be should be towards the right. It's not going to accelerate towards the left. In the vertical direction, our y-axis, we would have f sine theta, the vertical component of our pull force, plus the normal force going up, minus mg has to equal 0, because in this case it's not accelerating up or down. It should be just something sliding across the tabletop. Now, we can, at this point, make some substitutions to try to come up with a solution to this. It's not going to be quick and easy, but how about you plug in what the friction force equation is, and then we solve this formula for normal force. Let's see what we get there. All right, now a bunch has changed since I paused it there. So I solved the y equation for normal force, because I know that in my friction equation I need to know what the normal force is if I'm going to do any sort of work here. So I'm going to substitute that in for the F normal in the friction component of this equation. When I do that, I get this right here that I'm going to box in red, which has my pull force component that is going to try to make the thing move forward, minus the friction force, which is composed of the coefficient of friction, weight, and then the sine component of my pull force, should all combine together to be my net force in the x direction, which is going to be m times a. Now, you can again look at this from a standpoint of what if a variable changed. If this angle right here approaches 0 degrees, this pull force component is going to get bigger, and this sine theta component will get smaller. So I'm going to get a, it's going to not necessarily be a wash, but for small angle changes, the sine and the cosine change there are going to they're going to be close to eliminating each other. It's only once we get to larger angles where this cosine component starts to drop quickly and the sine component starts to increase quickly that we're going to get less and less force applied to the object, which is going to result in not much acceleration going forward. But you can play with those variables in your head a little bit to figure out what might happen in the future. So I'm going to stop this video here. This will be part 1, and we'll pick up with a part 2 video coming up soon.